Now we're moving on to look at proton nuclear magnetic resonance spectroscopy, so proton NMR. As I previously said, it's used to determine the structures of molecules and the exact position of functional groups in a compound. So previously we've looked at the more straightforward 13 carbon NMR. Now we need to turn our attention to proton NMR. As usual, we're using the reference molecule tetramethylsilane. You can see its structure here. This is the reference molecule, and when we compare the chemical shift of the carbons and hydrogens present in other functional groups, we'll always be comparing them to the TMS because by definition it has zero chemical shift. Now previously in carbon-13 NMR we said that the height of the peaks is totally irrelevant to what we're trying to find out. With proton NMR, by stark contrast, the area under each peak is incredibly important because it gives the relative number of hydrogen atoms in each environment. So here's a proton NMR spectra similar to the carbon-13. You've got your energy absorbed on the y-axis, you've got your chemical shift in parts per million on your x-axis. TMS shows your reference molecule with its zero chemical shift. Now what happens with proton NMR is you'll get what's known as splitting patterns. And these are caused by an effect called spin-spin coupling, and they give you information about the neighbouring hydrogen atoms. So these splitting patterns will tell you how many hydrogens there are on neighbouring atoms, and we use the n+1 rule in order to determine this. And I'll write this down for you shortly, but the n+1 rule states that the number of peaks a hydrogen signal is split into is one more than the total number of hydrogens on adjacent carbons. So here we can see 4 peaks, which means that the neighbouring atom must contain 3 hydrogens. Here we see 2 peaks, which means that the neighbouring atoms must contain 1 hydrogen. And if we start adding a little bit of detail here, look, sure enough, if you look at my colour coding, yes, this neighbouring atom contains 1 carbon. And if we look at my colour coding for the blue one, I said we'd expect the neighbouring atom to contain 3 hydrogens. Sure enough, the neighbouring atom here does contain 3 hydrogens. Proton MMR displays splitting patterns. These are caused by an effect called spin-spin coupling. The key thing though is that those splitting patterns provide information about the neighbouring hydrogen atoms. So basically, they're going to tell us how many hydrogens there are on neighbouring atoms using the n+1 rule, where the number of peaks a hydrogen signal is split into is 1 more than the total number of hydrogens on adjacent carbons. So, for example, if we apply this, we said that the number of peaks a hydrogen signal is split into is 1 more than the total number of hydrogens on adjacent carbons. So if the number of hydrogens on adjacent carbons is 0, by definition, the NMR signal will have a single peak. And we call that single peak a singlet. What about if there's 1 hydrogen on adjacent carbons? We can work this out with the n+1 rule. The NMR signal will be split into 2 peaks. With a tiny extra detail here in a 1-to-1 ratio, which we'll look at on NMR. And we call this situation a doublet. What about if there are 2 hydrogens on the adjacent carbon? This time the NMR signal will be split into 3 peaks in a 1-to-2-to-1 ratio, which we'll call a triplet. If there are 3 hydrogens on the adjacent carbon, the NMR signal will be split into 4 peaks in a 1-to-3-to-3-to-1 ratio, which we'll call a quartet. So to look back at what we've just discussed, the n+1 rule states that the number of peaks a hydrogen signal is split into is 1 more than the total number of hydrogens on adjacent carbons. So for example, if there are 0 hydrogens on the adjacent carbon, the NMR signal will have a single peak, which we'll call a singlet. If there's 1 hydrogen on the adjacent carbon, the NMR signal will be split into 2 peaks in a 1-to-1 ratio, and we call this a doublet. If there are 2 hydrogens on the adjacent carbon, the NMR signal will be split into 3 peaks in a 1-to-2-to-1 ratio known as a triplet. And lastly, if there are 3 hydrogens on adjacent carbons, the NMR signal will be split into 4 peaks in a 1-to-3-to-3-to-1 ratio, a quartet. And this goes on. If we had 4 hydrogens, we'd expect 5 peaks, 5 hydrogens, 6 peaks. Again, in your data booklet, you'll get some information regarding the chemical shift. This time, because we're looking at proton NMR, it's going to be a type of proton on the left-hand side of the table as opposed to the type of carbon. Now, the chemical shifts in proton NMR are smaller than the chemical shifts in 13 carbon NMR. The closer hydrogen is to an electronegative atom such as oxygen, nitrogen, fluorine, etc., the greater the chemical shift. So let's have a go at interpreting a proton NMR. As I've said, you'll expect your spectra to look very similar to your 13 carbon one with your chemical shift along here. Remember, it reads from right to left with TMS, your reference molecule, situated here. Just to look at the various peaks. So here you can see a quartet. According to the n+1 rule, you would therefore expect the adjacent carbon atom to have 3 hydrogens. Here we have a single peak, so you'd expect the adjacent carbon to have no hydrogens. Same is true here, no hydrogens. We've got 2 peaks here, so I'd expect the neighbouring carbon atom to have 1 hydrogen. Let's look at our molecule. I'm going to start at this end. Here we have 3 hydrogen atoms. Just to colour code, just to show you what we're looking at. The chemical shift here for these 3 hydrogens is between 0.7 and to 1.2. And the reason that this peak is split into 2, as we see here, is because, as I've written here, we're expecting 1 hydrogen on the next door carbon atom. And sure enough, the next door carbon atom has 1 hydrogen. If we move along to this hydrogen here, which is represented by the chemical shift here with 4 peaks, we've got 1 hydrogen showing a chemical shift between 3.1 and 3.9. The reason why that peak is split into 4 is because, as I wrote here, there are 3 hydrogens on the next door carbon atom. We call this a quartet, and yes, there are 3 hydrogens here. This red ink here represents this peak with a chemical shift of between 0.5 to 5, and we've written here that hydrogens attached to oxygen or nitrogen do not tend to show splitting patterns. They're represented by a singlet. Remember, the whole time you'll want to cross-reference with this table from the data booklet just to make sure you're happy with where these chemical shifts are coming from. And then lastly, the 3 hydrogens here located at between 2 to 2.9. As I've said, we've got no splitting here, and that's because, as I wrote here, there will be 0 hydrogens on the next door carbon atom. This is true, there's no hydrogens on here, so we're seeing a singlet. And then the extra thing, look, I pointed out that that was a singlet, and yes, it is a singlet, there's no splitting. Here with the blue, I already mentioned why we're expecting to see 4 peaks, and that's due to there being 3 hydrogens on the adjacent carbon. I said that that was known as a quartet. Yes, we can see that here. And then on top of that, we said that the ratio would be 1 to 3 to 3 to 1, and sure enough, the height of these peaks does show that ratio there. What about this orange one, which is a doublet? The ratio, we said, remember, would be 1 to 1, as you can see here, by the height of those peaks. Now, these numbers here, the numbers that have lovely colours, these are incredibly important. They're called integration values, and they show the relative number of hydrogens in each environment. Sometimes they'll be listed in a table, sometimes they'll just be written directly above the peaks. So here, 1 hydrogen has been split into a quartet by hydrogens on an adjacent carbon. Now, the integration values only show the ratio of hydrogens and not the actual number. This will become far more clear when we look at some past paper questions. Now, in proton NMR, CdCl3 or CCl4 is usually used as the solvent. The D is deuterium, which is known as heavy hydrogen because it contains an extra neutron. Now, neither CdCl3 or CCl4 contain hydrogen atoms, and therefore they give no signals in the spectrum. That's important. We don't want them disturbing the proton NMR. Now, CCl4 is nonpolar, so it's a good solvent for nonpolar organic molecules. CdCl3 is a polar covalent molecule, which means it's a good solvent for polar organic compounds. So obviously you'll pick your solvent based on what type of organic compound you have. Let's take another proton NMR spectra. Now obviously we have an ester here. Let's actually look at the splitting patterns on the NMR. So I've just grabbed the chemical shift data here from the table from the data booklet so we can actually have a look at what's going on. Starting with this CH3 here, we've got 3 hydrogens showing chemical shift from 0.7 to 1.2. Look, RCH3 0.7 to 1.2. So they're in the correct place on this x-axis. Now we have a splitting of 3 peaks, which means that the adjacent carbon to that CH3, according to the n+1 rule, must contain 2 hydrogens. Yep, there it is. That carbon next door has 2 hydrogens. Checking out its peaks now. So we've got 2 hydrogens with chemical shift of 2.1 to 2.6. So expecting it to be located next to that carbon double bond O. Because that carbon next door contains 3 hydrogens, according to the n+1 rule, that makes sense therefore that we have this quartet here. And then that has pinned down our C double bond O. What about this CH3 down here? We have a chemical shift of 3.7 to 4.1 due to the ester linkage. Look at the data here. And the next door atom has no hydrogens on it, which is why you see no splitting of this peak. We have simply a singlet. Now, this is an isomer, and the biggest thing I want to point out here is notice how the different isomers produce different proton NMR spectra, and that's due to the different hydrogen environments and splitting patterns. So despite the fact that obviously they have the same molecular formula, they're both esters, you still see different splitting patterns. So you can see how the proton NMR is very helpful in determining the order of these atoms. So diving in here where we have a quartet, yes, you can look at the chemical shift here, but the one thing I want to point out is because that is a quartet, the next door carbon must have 3 hydrogens due to the n+1 rule. Yes, here it is. Here's our triplet as represented here. And that therefore accounts for the differences we see between these 2 isomers NMR. Now, spin-to-spin coupling is not seen when equivalent hydrogens are on adjacent carbon atoms, nor when a hydrogen is attached to an oxygen or a nitrogen, which is something I previously mentioned, so we can't see any splitting here. And so as a result, the spectrum for this ethane 1,2-diol has simply 2 singlet peaks. And one last thing to point out is that these peaks, these integration values, only show the ratio of hydrogen atoms, not the actual number. This question is about NMR spectroscopy. A compound is usually mixed with SiCH34 and either CCl4 or CdCl3 before recording the compound's proton NMR spectrum. State why these 3 compounds are used and explain how their properties make them suitable. Let's start with tetramethylsilane is used as a reference molecule as it shows 0 parts per million chemical shift. What other properties make it useful for this purpose? TMS is unreactive, it's inert, non-toxic, and easy to remove from the sample. How about CdCl3 and CCl4? Well, these are both used as solvents. The ideal thing about both of them is they give no signals in the spectrum because they have no hydrogen atoms. And let's go in now really precisely saying when you'd use each type of solvent. So CCl4, remember, is non-polar, so is a good solvent for non-polar organic molecules. And then CdCl3 is polar, and therefore it's a good solvent for polar organic compounds. Deduce the splitting pattern for each of the peaks given by the hydrogen atoms labelled X, Y and Z in the proton NMR spectrum of the compound shown. I've just set myself up for the rest of this question by pulling in the chemical shift data from the data booklet, and then I've drawn out the displayed formula so we can see more clearly what will be going on here. So if we look at X, which is CH3, according to the N+1 rule, just have a look at the next door atom, the carbon. It has one hydrogen atom attached, so according to N+1, we'd expect to see a doublet here. Remember, that would tell us, therefore, that the neighbouring carbon has one hydrogen, as is the case. So moving on now to Y, right, obviously there are two adjacent carbons. There's no hydrogens on this carbon, however, so we would expect no splitting caused by that. However, over here, we have three hydrogens, so according to N+1, we'd expect this hydrogen to be split into a quartet. And then last but not least, Z. Because they're in the same environment, it doesn't matter which one you look at, but obviously the neighbouring carbon has one hydrogen on it, so therefore the hydrogens would be split into a doublet. Suggests why it's difficult to use table B, so this table here, to predict the chemical shift for the peak given by the hydrogen atom labelled Y. Well, that's because this hydrogen is attached to both a carbon chlorine and a carbon oxygen. So if we look here, look, that would be relevant because it's carbon attached to chlorine. This would be relevant because it's carbon attached to oxygen, but there's no set of atoms which shows both. Two isomers of blah each have two singlet peaks only in their proton NMR spectra. In both spectra, the integration ratio for the two peaks is 2:9. Deduce the structures of these two isomers. Okay, the first thing I want to do is work out the molecular formula. So we have 6 carbons, 11 hydrogens, a chlorine and an oxygen. Now the integration ratio is 2:9, which adds up to 11. Which is super handy because we know we've got 11 hydrogens altogether. So actually that tells us straight away that we have 2 hydrogen environments. One with 2 and the other one with 9. And that singlet tells us that both of them must be attached to a carbon with no hydrogen, otherwise you'd expect splitting. So based on all of that, we know we must have this layout of atoms. And so to actually apply what I just said in terms of a structure, look, this is the only structure that works. Why? Because here we have 9 hydrogens. They're clearly all in the same environment and they're attached to a carbon with no hydrogens. So thus far we have obeyed all the information here. Next up, we need 2 different ways, because we've got 2 isomers, of including a C double bond O and a Cl. So if we think about the possible homologous series, it's likely to be an acyl chloride and a ketone with a chlorine group elsewhere. And then finally, we need to fit in our remaining leftover atoms of CH2 so that the hydrogen will not be split, and therefore we know that that must be next to a carbon with no hydrogen. So I'll show you the structures and then I'll kind of explain it again from the structural point of view. And remember, with these sorts of questions, there's always an element of trial and error here, so you must take your time to try out different arrangements of atoms. So here's our acyl chloride. So just to show you, 3, 6, 9, 10, 11. Yes, we've got 11 hydrogens. In terms of the environments, they're all one environment. Wonderful. These are in a second environment. There's 2 hydrogens. Yes, great. And then just to show that we've got 2 singlet peaks, if I focus in on here, let's have a look at the neighbouring atoms, both of these carbons. Look, neither of them have hydrogen attached, so that's great. That gives me a singlet peak here. So if we look at our second singlet peak, focusing in on this hydrogen environment, sure enough, the neighbouring adjacent atom, this carbon, has no hydrogens attached to it. So I'm very happy with my acyl chloride structure. And then my second isomer is a ketone. Okay, so looking again, yes, we have 11 hydrogens. Yes, we have 2 environments. One has 9 hydrogens. The second one has 2. Perfect. What about these 2 singlet peaks? Looking at this carbon here, sure enough, the adjacent carbon has no hydrogens on it, so that would produce our singlet peak. And then what about this carbon here? No, neither of these atoms have a hydrogen attached, so perfectly happy with both of my isomers. Figure 3 shows the proton NMR spectrum of Q, which has a molecular formula of C3H7ClO. The table below shows the chemical shifts and integration values for each peak. Deduce the structure of Q and explain your answer. I'm going to start by looking at the integration values. Remember, this tells us the relative number of hydrogens in each environment, so we need a ratio here. So in effect, you want to divide each of these 3 numbers by the smallest number, which is 0.6, to get a ratio of 1 to 1 to 1.5. Let's get a whole number ratio, 2 to 2 to 3. So what that means is that the first environment contains 2 hydrogens, the second environment contains 2 hydrogens, and the third environment contains 3 hydrogens. And we know that ratio corresponds to the exact number of hydrogens in this compound, because actually here it tells us that there's 7 altogether, so that makes this question slightly more straightforward. And let's look at the chemical shift data now. So we know we've got a peak at 3.95. I've pulled in the data from the data booklet. So 3.95, look down here, could obviously correspond to this type of proton and this one here. Again, bear in mind your molecular formula, it contains a chlorine, so it's highly likely therefore that 3.9 corresponds to RCH2Cl. So I'm just going to write that there. Because that's the highest chemical shift, it means that it is this triplet here, and because that's a triplet, according to the n+1 rule, it tells me therefore that there's 2 hydrogens on the neighbouring carbon. Let's have a look at this chemical shift data here, 3.65. Again, look down here. Now it's likely to be the ROCH, again, because we've double checked with our molecular formula. Yes, we do need an oxygen in there. And then because of this integration value here, I know that I've got 2 hydrogens in this particular environment, so I can just add a H here. And then looking here with this chemical shift of 3.35, it does actually fit as being ROCH again. And that makes sense because obviously that oxygen does need to be bonded to atoms either side of it. And because we have an integration value of 3, that tells me that I have 3 hydrogens in this environment. So now we've worked out the individual pieces, we can start to fit them together in the puzzle. I'll start here just because I know the chlorine can only ever have 1 bond. And I know that the chemical shift here relates to this triplet here. So I'll expect, due to the n+1 rule, there to be 2 hydrogens on the neighbouring carbon. So that makes me look at this set of atoms. Obviously, this corresponds to this triplet here, as I would expect, because it's a triplet next door. Due to the n+1 rule, we'd expect 2 hydrogens on this structure. And sure enough, here are 2 hydrogens. And then we get to complete our molecule over here, which corresponds to this peak. And again, that makes sense. It's a singlet, which means that the next door atom shouldn't have any hydrogens on it, and sure enough, it doesn't. So now let's write our full explanation. So just pointing out everything I've already mentioned, our integration ratio was 2 to 2 to 3. Just to remind you, that means that we had 2 hydrogens, and 3 hydrogens in the various environments. What about our peak at 3.95? Is a Cl to CH2 next to a CH2. I'm just pulling this out from the structure I've drawn. And how do we know that? Because from the NMR we can see it's a triplet. Let's do the exact same thing here for the 3.65. We know that that's an OCH2 next to a CH2, as it's a triplet, and therefore it must be next to a carbon with 2 hydrogens. And then lastly, our chemical shift here with 3.35 is also an oxygen CH3. We can see that it's a singlet from the proton NMR, which means that the adjacent atom can't contain any hydrogens, as we see here. So we're just going to point that out. So to summarize, what did we do? We used the integration value to determine the number of hydrogens in each environment. Luckily, they added up to 7, so we could actually use that as an exact number. We used the chemical shift data to determine the likely type of proton. We also used the peaks, the fact that that was a triplet, which meant that the adjacent atom must contain 2 hydrogens. Again, that was true for this one. The adjacent atom must contain 2 hydrogens. And then this singlet here told us that the adjacent atom, in this case the oxygen, must contain no hydrogens.